Welcome to the World of Chemistry YouTube channel. Today we will discuss about the developments leading to Bohr's model. So this is one of the most interesting topics in atomic structure. Developments leading to Bohr's model. So you already know Rutherford's atomic model. Although Rutherford explained the presence of a nucleus, his model could not explain why electrons do not lose energy and fall into the nucleus. Scientists therefore searched for new ideas and discoveries to solve this problem. So they found four important discoveries that helped Bohr develop his atomic model. So the first one is electromagnetic waves, Planck's quantum theory, photoelectric effect, atomic spectra. Now let us understand each of these step by step. So at the end of this lesson, you should be able to explain electromagnetic waves, define the wavelength and frequency, okay, understand Planck's idea of quantized energy, explain the photoelectric effect, and understand the atomic spectra. So finally explain how all these discoveries helped Bohr develop his atomic model. So you have to explain all these, able to explain all these points. Okay. Now these concept maybe seems to be different, but all of them are connected and lead to Bohr's model. Okay. So now before Bohr proposed his model, Rutherford's model was accepted. However, there was a major problem. According to classical physics, an electron moving around the nucleus should continuously lose energy. So, according to classical physics, an electron moving around the nucleus should continuously lose energy. If it loses energy, it should spiral into the nucleus. If it loses energy, it should spiral into the nucleus. But atoms are stable. They contradiction puzzled scientists. So this contradiction puzzled scientists. To solve this mystery, scientists studied the nature of light and energy. Their discoveries eventually led to Bohr's model. Okay, so now what are electromagnetic waves? What are electromagnetic waves? Let us begin with electromagnetic waves. So energy can travel from one place to another in the form of waves. For example, sunlight reaches earth from the sun. For example, sunlight reaches earth from the sun. The space between sun and earth is almost vacuum. The space between the sun and the earth is almost a vacuum. Still, light travels through it. How is this possible? How is this possible? Because light is an electromagnetic wave. Electromagnetic waves do not require any material medium to travel. Electromagnetic waves do not require any material medium to travel. They can travel through empty space. So, electromagnetic waves can travel through empty space. Example include radio waves, microwaves, visible light, X-rays and gamma rays. An electromagnetic wave consists of two fields. One is electric field, another one is a magnetic field. So these two fields oscillate continuously. So electromagnetic wave consists of two fields. One is electric field, another is magnetic field. These two fields oscillate continuously. The electric field and magnetic field are perpendicular to each other. They are perpendicular to each other. Both are also perpendicular to the direction of wave. Both are also perpendicular to the direction of wave, the direction of the wave traveling. So this whole arrangement allows electromagnetic waves to move through space carrying energy. This whole arrangement allows electromagnetic waves to move through space carrying energy. To understand waves, we must learn two important terms. The first is wavelength. Okay, wavelength is the wavelength is the distance between two consecutive crusts or troughs. The wavelength is the distance between two consecutive crusts or troughs. So it is represented by the lambda. Okay. The second is frequency. Frequency is the number of waves, the number of waves passing through a point in 1 second. Frequency is the number of waves passing through the point in 1 second. It is represented by nu. Okay, the unit of frequency is hertz, Hz. So higher frequency means more energy. Higher the frequency means more energy. So the relationship between frequency and wavelength. So what is the relationship between frequency and wavelength? The speed of light is represented by c. The speed of light is represented by c. It is equals to, the c is equals to lambda into nu, where c is the speed of light, lambda is the wavelength, nu is the frequency. Since this c remains constant, when the wavelength increases, the frequency decreases. When wavelength increases, the frequency decreases. When wavelength decreases, frequency increases. Therefore, wavelength and frequency are inversely proportional. So wavelength and frequency are inversely proportional. If, if a wavelength becomes very small, what happens to frequency? If wavelength becomes very small, what happens to frequency? So what happens? The frequency increases. Okay, the frequency increases. So now waves occur electromagnetic waves occur over a wide range of wavelength wide range of wavelengths. This entire range is called the this entire range is called the electromagnetic spectrum. Electromagnetic spectrum. So it includes radio waves, microwaves, infrared rays, visible light, ultraviolet, X-rays and gamma rays. So visible light, this, this visible light occupies only a small portion of spectrum. This visible light occupies only a small portion of the spectrum. As frequency increases, as frequency increases, the energy also increases. As frequency increases, the energy also increases. Now we move to the next important scientist, Max Planck. Max Planck. So scientists were studying black body radiation. Scientists were studying black body radiation. Classical physics could not explain the observations. Classical physics could not explain the observations. In 1900, Max Planck proposed a revolutionary idea. Max Planck proposed a revolutionary idea. His idea completely changed our understanding of energy. Our understanding of energy. Planck suggested that energy is not emitted. What Planck suggested? Energy is not emitted continuously. Instead, energy is emitted in tiny packs. Energy is emitted in tiny packets. These packets are called quanta. These packets are called quanta. Okay. Think about climbing the stairs. Think about climbing the stairs. You cannot stand halfway between two steps. You cannot stand halfway between the two steps. You move step by step. You move step by step. Similarly, atoms absorb or emit energy in fixed amounts, not continuously. What happens here? Atoms absorb or emit energy in fixed amount, not continuously. So this idea is called quantization of energy. This idea is called quantization of energy. Planck proposed the equation that is E equals to h nu, where E is the energy, E is the energy, h is a Planck constant, nu is the frequency. This equation tells us that energy is energy is directly proportional to frequency. This equation tells us energy is directly proportional to frequency. Higher the frequency, higher the energy. H is constant. So energy is directly proportional to frequency. Higher the frequency means higher the energy, lower the frequency, lower the energy. Planck's theory was extremely important. Planck's theory was extremely important. For the first time, scientists understood that energy exists in discrete packets. So, scientists understood that energy exists in discrete packets. This became the foundation of quantum mechanics. This became the foundation of quantum mechanics. Later, Bohr used this idea to explain electronic energy level. Later, Bohr used this idea to explain the electronic energy level. So let us now study the photoelectric effect. When, when light falls on certain metal surfaces, when light falls on certain metal surfaces, electrons are emitted. Electrons are emitted. So this phenomena is called photoelectric effect. So the emitted electrons are called photoelectrons. What happens when light falls on certain metal surfaces? The electrons are emitted. So these emitted electrons are called as photoelectrons. Okay. Scientists observed several interesting facts. First, electrons are emitted immediately. So what are the facts here? The electrons are emitted immediately. The second one is light must have minimum frequency. The light must have minimum frequency. The third is increasing the light intensity. Increasing the light intensity increases the number of electrons. Increasing light intensity increases electrons energy, number of electrons. The fourth one, increasing the frequency increases electron energy. Increasing the frequency increases electron energy. So these observations could not be explained by classical wave theory. So these facts are not explained by the classical wave theory. Albert Einstein solved this problem. He proposed that light behave as a tiny particles. Light behave as a tiny particles called photons. Called photons. Each photon carries a energy. Each photon carries a energy. The photon energy that is equals to h nu. When a photon strikes a metal, when a photon strikes a metal surface, it transfers it transfers its energy to an electron. It transfers its energy to electron. If the energy is sufficient, if the energy is sufficient, the electron escapes. The electron escapes. So photon energy is equals to work function plus kinetic energy. The total energy brought by the photon pays the cost to break the electron free, and whatever is left becomes the electron's speed. Electron's speed. So this experiment proved that light has a particle nature. The light has a particle nature. It strongly supported Planck's quantum theory. Planck's quantum theory. So Einstein received the Nobel Prize for this work. Okay. So this discovery became the another step towards a Bohr atomic model. Bohr atomic model. Now we come to the most important discovery that atoms, when atoms absorb energy, electrons move to higher energy. Electrons, when atoms absorb energy, electrons move to higher energy levels. So such electrons are called excited electrons. So these excited electrons are unstable. These excited electrons are unstable. They return to lower energy levels and release the energy as light. What happens here? When atoms absorb energy, electrons move to higher energy levels. Such electrons are called excited electrons. These excited electrons are unstable, so they return to the lower energy levels and release energy as light. When hydrogen gas is excited, when hydrogen gas is excited electrically, when hydrogen gas is excited, it emits a light. It emits a light passing through this, passing this light, passing this light through a prism. Through a prism, it produces several bright lines. Several bright lines. These lines are called line spectra. These lines are called line spectra. Unlike a continuous spectrum, only specific wavelengths are observed. Only some specific wavelengths are observed. This indicates that atoms emit atoms emit only specific energy. From this we understood that the atoms emit only specific energies. So scientists classified hydrogen spectral lines into different series. Okay, scientists classified hydrogen spectral lines into different series. The first one is Lyman series. Lyman series, where the falls electrons falls to n equals to 1. N equals to 1. Then comes Palmer series, where electron falls to n equals to 2. Then Fastson series. Fastson series, electron falls to n equals to 3. Bracket series, electron falls to n equals to 4. Then comes Fun series, electron falls to n equals to 5. So each series corresponds to specific energy transition. So here each series corresponds to the specific energy transition. Atomic spectra provided direct evidences that electrons cannot possess any arbitrary energy. What happens here? The atomic spectra provided direct evidences that electrons cannot possess any arbitrary energy. They occupy only specific energy levels. So this observation became the strongest experimental evidence for Bohr's theory. So this observation became the strongest experimental evidence for a Bohr's theory. Let us connect, let us connect everything together. Now let us connect everything together. Electromagnetic waves helped scientists to understand the light. Planck showed that energy is quantized. Einstein proved that light consists of photons. Atomic spectra showed that electrons occupy fixed energy levels. Atomic spectra showed that electrons occupy fixed energy levels. Using all these discoveries, Niels Bohr proposed his atomic model in 1913. It is called Bohr's atomic model. Okay, Bohr's atomic model. So, till now we discussed electromagnetic waves carry energy. Wavelength and frequency are related by C equals to lambda nu. Then Planck proposed a quantized energy. Einstein explained the photoelectric effect using photons. Atomic spectra revealed fixed energy levels. So these discoveries led to the foundation for Bohr atomic model. So thank you for your patience and listening to the class. Please visit for the next video. The channel is World of Chemistry. Thank you everyone.